also welcome everyone, and also thanks for joining, taking some time of your busy schedules to join this session. My name, as you see on the screen, is Dario Rodriguez. I started with SKF back in Argentina a bit more than 36 years ago, and after working some years in Sweden, where we had our headquarters, and also in Singapore 6 years, and now in Australia. So for the last 2 years, I am based in Western Australia in the city of Perth. And my experience has been always in engineering roles and working with all different type of industrial customers we have. And one of my, I would say, key activities has been helping customers to understand the reasons for bearing failures as the initial step in trying to improve reliability and increase productivity, efficiency, reduce environmental impact, and many other aspects that are applicable to different assets. So without further ado, let me go into the subject of today. We are not going to be able to become experts in bearing failures in just 45 minutes, that you can think. But we will try to cover the basics, the most important ones, and we will see some examples of how bearing surfaces look like, because the failure interpretation is initially a visual interpretation, which is explained in this ISO standard. We will not cover the complex cases, but we are going to give you an idea of what are the required skills and knowledge when you do these bearing investigations. If we can talk about what are the most common cases of bearing failures, we can see some numbers, and I can tell you upfront that the numbers are going to be different depending on the source, depending on your own experience, depending on the type of bearings and assets and environment. But in general, we see that independent of all these factors, the most common reasons for bearing failures are roughly the same. We can say, for example, material fatigue, and material fatigue can be seen as a normal failure mode on which the bearing life and the bearing selection process is based on, but it can also be a consequence of abnormal stress applied to the bearing due to things like misalignment or oval support surfaces like the shaft or the housing, excessive unbalance, excessive belt tensions, or even choosing the wrong bearing for the job. Then we have lubrication-related issues. And of course, there are many things under this umbrella of lubrication, but we can mention just a few, like not choosing the right lubricant for the job because it's not the right viscosity or the right consistency or doesn't have the right additives. And it can also be that the correct lubricant is applied incorrectly, like an excessive amount or an insufficient amount, or not correct replacement or relubrication intervals. We also have contamination down here. So this represents a bearing working in a tough environment where they may be different source of contaminants, whether they are particles or they are liquids, corrosive media. There may be many different conditions that the bearings are not protected properly from, and they also, in a way, will affect the lubrication, and by affecting the lubrication, they lead to a failure. Then we can mention many other situations. The 16% on the right covers many other possibilities. We could have, and we have seen many times, bearings that are not taken care properly during storage or during transportation. And then the bearings have conditions for failure even before they start operation. You could also damage the bearing after installation when you are installing some of the component on the same shaft. To give an example, you might be installing a pulley on a shaft and you are doing that supported by the bearings on the same shaft, and then you may damage the bearings in the process. So these, again, are numbers that will change depending on your assets and your specific industry and environmental conditions. And one of the things, I mean, too late, what do we mean by this? Probably the picture is quite self-explanatory. But if we are going to remember just a couple of things from today's session, because the material is there will be literature that we will mention at the end of the session. But if we are going to remember just a couple of things, one is that only when the failure is detected and investigated at an early stage, we have a chance to understand what was the initial condition that led to the failure. And then we are going to be able to identify what do we need to correct for avoiding that to happen again. And the second point that we want to emphasize as, let's say, one of the key learnings to remember from today's session, and we use the analogy of the leaves or the tree and the forest. So what do we mean by this? Many times, some of the, let's say, evidence that helps you to identify and confirm a failure hypothesis are on the components around the bearing, and therefore they are not limited to the bearing itself. For example, we need to look at the shaft, at the housing, at the covers of the housing, the seals, the seal surfaces, the lubricant, the foundation, and any other element, and even the bearing that was mounted at the other end of the same shaft. So we should never look at the bearing, at the details of the bearing in isolation. The bearing is part of a system, and it has to be looked in that context. We should remember some very basics, and I know most of you will find this very familiar. But this is important to make sure that we understand what we see, what might be considered as normal or abnormal from, let's say, a bearing that has been in operation properly, and from one that has not. So where do we start? Well, of course, bearing terminology. I mean, most of us are not going to be doing a bearing investigation just for our own interest. We are going to be doing that as part of an evaluation of a situation that others will be involved, which means that we are going to have to issue reports, and it's important that others will understand and understand the terminology and exactly what we are referring to. So there is internal geometry on the bearing as the basis to know when we are describing something, where is it, how does it look normal or of not normal, depending on the design and characteristics of the bearing on the surfaces that we are examining. There are many other bearing types, of course. Different bearings have even different number of internal components and configurations, and we need to take that into account. We need to consider these differences when trying to interpret the symptoms and the normal patterns from the abnormal patterns. And you can even say that there are differences between different bearing suppliers in terms of the internal design, which are also have to be taken into account for a proper interpretation. Let's look at some of these components, like the cage, which are made, as we can see, of different materials, brass, pressed steel, or polyamide cages. This is just an example of the difference between different bearing types that will have different cage designs. And also within the same bearing type, you may have different cage types and designs of within different sizes of the same bearing. There are different cages that, for example, they interact with the rolling elements, the balls or the rollers, or with the rings in different ways, depending on their configuration within the bearing. This means that a cage will have some normal contact areas, while other surfaces are not supposed to be in contact. If we don't understand the design of a bearing, it will be difficult to judge if the evidence of some contact in a particular surface of the cage is supposed to be there or not. Let's look at this example. These cages represented in yellow color are representing brass cages. And brass cages can be produced with a geometry that will not touch under normal conditions the inner ring shoulders, not the inner ring, not the outer ring. So they are called rolling element center or rolling element guided cages. While in other cases, the cage is resting. The cage might not be exactly as it's drawn here. This is just for simplification. But the cage may be resting its weight on the shoulders of the inner ring of this ball bearing. So it's an inner ring guided, or the opposite can happen, that is guided on the outer ring shoulders. So those are characteristics that we need to know, so we are able to differentiate which surfaces are the normal contact areas from the ones that are not. Locating and non-locating bearing arrangements. This is again a quite basic concept of bearing applications. It's important to understand the bearing, like I said before, as part of a system. So in most bearing arrangement, maybe not in all of them, you will find this combination of locating, non-locating position. And if you, let's say, are looking into a failed bearing, one of the things you need to ask is the failure on the bearing in the locating or the non-locating position? Because, as for example, in this case, we have the same bearing type and size on both positions. So if we don't ask, if we have not identified from which position this bearing that we are looking at is coming from, we wouldn't be able to answer that. And then if we have an indication of an axial load that was acting on that bearing, we would need to ask and be able to answer if that bearing was in the non-locating position, because if it was, then that is abnormal. The bearing in the non-locating position was not supposed to take the axial load, and then we will need to find and start thinking about possible reasons for that to happen. Now let's look a little bit into load patterns. What do we mean by load patterns? What do we mean here is which are the areas where the bearing, even under normal lubrication and operating conditions, will have evidence of rolling motion. There will be some change in the asperities of the surfaces, in the roughness, very, very mild, but enough to identify that there was contact in those areas. In this picture, what we see is a bearing that has an inner ring rotation. The outer ring is stationary. So in this example, what we see is that for a given load applied through the shaft onto the inner ring, the bearing will exhibit a load area of about 150 degrees, which will basically indicate that because the inner ring is rotating, it will have a load pattern all around the inner ring raceway, covering, of course, 360 degrees. While the running elements, the balls or the rollers, will go through, they are not working all at the same time. And in this case, also to be clear, we are discussing a typical case of an horizontal mounted machine with a single row ball bearing. So in this case, we can say that the balls or the rollers are only going to be loaded when they go into the area where the load is acting. While the outer ring will only be working in this load area where we see the smaller green arrows that are of different magnitude, which is also indicating that the load magnitude is not the same for the outer ring in this region. So there will be smaller, let's say, wider contact area towards the maximum load and is tapering off towards the entry of the load zone or towards the end of the load zone. That will be a characteristic feature of the load pattern on a bearing under these conditions. And this is an example of an application where we can identify these operating conditions. This will be, let's say, the shape wheel or even the wheel of a crane in an application where we have two spherical roller bearings, locating position, non-locating position, where we have a rotating shaft, which is rotating with the inner rings, which are mounted with interference feet. And we can say that in this drawing, we can clearly identify that the bearing that we call non-locating position is because there is a space for the outer ring, this stationary outer ring, which is not rotating, of course, and then it has the possibility to displace in axial direction when the temperature differences are requiring the bearing to do so. So we can say if we are going to examine any of these bearings, we will need to understand which bearing was mounted in which position, and even in which positions each of the rings was located within its own housing or shaft. So if we look at that case, we will see something like this. Of course, this is simplified to a ball bearing in the picture, and the bearing we saw was a spherical roller bearing, but the principle is the same. So we have a rotating inner ring, as indicated here, a constant load direction, the stationary outer ring, which is only loaded in an area of around 150 degrees. And when we look at these bearings, we will see, for example, in this case, a single row ball bearing with a constant load pattern on the inner ring raceway in the center, which has a constant width. And the width of this pattern will change depending on the magnitude of the load and to some extent also on the internal clearance available in the bearing when it's mounted. But on the outer ring, we see here that what we described before, that the load pattern is widening towards the area of maximum load and is tapering off towards the start or towards the end of the load area. And the rolling elements, the balls in this case, will have, let's say, quite even load pattern all around its surfaces, because they go through the load area as they are rotating and orbiting around the bearing. This was just one example, of course. There are many other possible combinations of bearings that have outer ring rotation, bearings that have axial load on a radial bearing, or like in this case on the right-hand side. We can have combined loads where there is axial and radial load acting simultaneously. And we can have even load patterns that are already indicating some kind of abnormality. Like, for example, if we see misaligned patterns on the raceways of our bearings, it might be an indication that the bearing was not properly installed, that there was some misalignment between the inner ring and the outer ring on a bearing that is not supposed to be exposed to that condition. You can have out of shape supports or excessive interference. For example, if the bearing is left without internal clearance in operation, we might see a full contact pattern also on the outer ring that is not supposed to be there for certain bearing types at least. So again, there are many possible combinations, and that's why we need to be very careful in looking at all the components and trying to link them back to the application and the operating conditions to understand if what we are looking at is supposed to be like this or not. So now let's go into the specifics of the ISO 15243, which was updated. Initially, was released in 2004, and then it was there was an update in 2017 to align some definitions. The ISO classification is basically a joint effort of different bearing manufacturers on the terminology to identify the most clear and direct failure modes. It does not cover everything, and it's limited to failures in service. That means that, for example, transportation, storage, and some other failures that might develop before the bearing starts operation are not mentioned there, even though in some cases they look very similar or even exactly the same as failures that can happen in operation. The ISO classification will help us to, to choose, I would say not to understand, but to choose the correct failure mode that we are going to use in our reports when you do a bearing investigation, of course. But by no means we should take this as these are all the failure types, and we should find a way to link our failure to one of these classifications. There will be cases that is not possible, and that is part of the normal process of identifying the failure. It is also important to understand the criteria regarding that the ISO refers to the most visible change in appearance. This is something that you should be able to see with your own eyes, or even with a small magnification in some cases. The typical example of that is that we tend to identify a fracture on a ring as the main failure, and we see that fractures are mentioned. But the fracture, in most cases, could be the consequence of something else that was happening in the bearing, like we will see examples of. And therefore, if you focus on the fracture, you might not be focusing on the proper, let's say, failure mode that you can act on, that you can work to solve, because the fracture, again, was a consequence and not the cause. So let's see some examples. And what we are going to use in the following pages is pictures, representations, 3D representations of the bearings to which the picture belongs to. So this is an inner ring of a single row deep groove ball bearing. And we are pointing towards the area of the surfaces that are representing the failure in this case. So the first ISO failure type is the subsurface fatigue. And the bearing is damaged, you can say, as the first indication of a failure happens. It can be flaking and spalling, and it can also be other things. But this does not mean that the bearing cannot continue to operate even with this small failure. But what we need to understand is that the longer we allow the bearing to continue to operate, the harder it will be to identify what was the original reason. So basically, in this case, if we allow the bearing to continue to run, this will expand. It will start to show all around the bearing and in the other components, and then how we are going to be able to identify that this problem started by material fatigue. It will be very hard, if not impossible. The subsurface initiated fatigue, like we see in this outer ring, this is an outer ring of a self-aligning ball bearing. And what you see in this picture is the ring shown in front of a mirror. So basically you can see the opposite area of the raceway. And we see two opposite areas that are having a damage. And the damage is also by subsurface fatigue. So the reason why we are representing this case here with an oval housing, so the bearing has been squeezed into areas that are 180 degrees apart, is because the subsurface fatigue is a consequence of the level of stress on the material and the number of cycles, which are the number of times the balls or the rollers are going through that area with high stress. So we can basically overload the bearing in different ways that are not normal and also create a subsurface fatigue failure mode. So we can say this is not normal. This subsurface fatigue should not have happened if the ring was not mounted on an oval housing. In this case, what we see is the representation of surface-initiated fatigue. And this one on the inner ring of a spherical roller bearing may be a bit hard to distinguish with the naked eye, because these surfaces look gray and dull. But when you look with some amplification, you start to see small cracks and micro-spalling. Some people will also call this surface distress or micro-pitting. And the reason for this is usually related to a poor lubrication condition, which basically increase the surface friction, and that basically leads to these small cracks and micro-spalling to form. We have seen also that in some cases, lubricants that have very aggressive EP additives, when they are exposed to high temperatures, they might attack, they turn acid and they attack the bearing material, leading to a weakening of the surfaces and creating this type of damage. So basically, we always recommend to use proven lubricants or lubricants that have proven EP additives. Another failure within this ISO classification is abrasive wear, and this is very interesting. It's also the inner ring of a spherical roller bearing, and what we can say here when we look at this picture is that there is a tremendous asymmetry between the right and the left hand side of the same inner ring. And basically what we see is that all this material has been removed. So you can basically in this example see that the bearing can even continue to work with this level of wear. But of course, this was a progressive process. What is interesting in this case is that the asymmetry is associated to the operating conditions to which the bearing was exposed to. So what do we mean? That in this case, the bearing was mounted on a vibrating screen where the outer ring is stationary, the inner ring is rotating, and the load is rotating with the inner ring. So they are, we can call it in phase, or they are rotating together. So you can say that in this case, even if the inner ring is rotating, it's always exposed to load in the same area. And when you add to that, that there was a significant amount of contaminants going into the bearing, mixing with the lubricant and transforming the lubricant into an abrasive media, then we create the perfect conditions for this to happen. And in this example, we see abrasive wear on the brass cage of an angular contact ball bearing. And you can see on the picture on the left that the cage is completely separated into two parts. And you can even notice some of the burrs in the border of the contact with the balls. And even the balls look a golden color because of the amount of brass material that has been deposited on the surfaces. So the cage is, no question, one of the weakest elements of the bearing, and is not supposed to do an extremely difficult job under normal operating conditions. But when things go wrong, in this case with the lubrication contamination, they can suffer greatly because they are going to be much softer than the material of the rings and the running elements. In this other example, we see another form of abrasive wear. We call it polishing wear. And the characteristic feature here is that you see that there are bands in this inner ring of, again, a spherical roller bearing. There are very shiny bands and also very brownish and some dark discoloration bands. So one of the things that, for example, this is teaching us is that the surfaces will, in some cases, under poor lubrication conditions, there is a lot of metal-to-metal contact. So initially, the surfaces tend to polish themselves. So the roughness seems to be even lower than the original manufacturing range. And the temperature on the surfaces start to increase. So you see these brownish areas that are generally the deposits of some of the additives being, let's say, exposed to high temperature on the surfaces and reacting with the surfaces. But the other element that we need to understand is that what we see on the raceways is also not only the interaction of the running elements with the raceways, in this case the inner ring, but it's also the interaction of the running elements with the cage, that is also transferred into the raceways. So the contact pattern is a combination of the interaction of the different surfaces within the bearing. This one is the what we call adhesive wear, and basically what is happening here on this outer ring, again of a spherical roller bearing, we see this as the entry of the roller into the load area. And what has happened here is that the roller has been accelerated because it was rotating on its own axis much slower than the speed it is supposed to have by the rotation of the inner ring. So to make a simple analogy here, we can think of the wheel of a car or a motorcycle on the road when you accelerate very fast and then you spin the tire on the tarmac. So something similar can happen in the bearing. Usually when the bearings are having some improper lubrication in combination with light loads, very, very light loads, and high-speed operation. And this type of adhesive wear can also happen, for example, between the flanges and the rollers on cylindrical roller bearings and on taper roller bearings. So what we see here is some example of those surfaces. And what is the issue here? That these surfaces are exposed to sliding. There is no rolling like on the main load areas of the bearing. So these areas are extremely critical from a lubrication point of view because of the significant amount of sliding that happens under normal operation. So they are prone to have this when the viscosity is not right, the lubricant is not in the right quantity, or it's not replenished at the right time. Moisture corrosion. This is, for some industries, I would say, is a classic. We can think of the paper making industry, where there is a lot of areas with a lot of water. And when the seals of the bearing housing and the arrangement of the seals is not good enough, or has been worn out, or there is some other issue, the corrosive media enters, and then what we see in this picture, again in a ring of spherical roller bearing, is that we see a certain pattern in the distance between these marks. And then when you overlap the cage here, you will see that the distance is exactly the distance between the rollers of the roller pitch. So this indicates that this was happening at the time that the bearing was not in operation. So it's not uncommon that when you have a contaminated lubricant with, for example, water, the damage will be probably worse when the bearing is not in operation as compared to the damage that you have when the bearing is in operation with the same proportion of water in the lubricant. More examples of, again, inner ring and, in this case, outer ring of spherical roller bearings with corrosion with the same roller distance. Again, typical of paper making machine applications, but in many other industries where the bearings are exposed to washing, the machines are exposed to washing and other significant temperature variations in a short period of time, which generates condensation. What we see here is a fretting corrosion. Fretting corrosion is a phenomena that develops, in this case, in the outer surface of the outer ring, but can also develop between the inner ring and the shaft. Usually, it's more common on rings that are mounted with a loose fit and exposed to load. It's not, we do not mean here that mounting a bearing with a loose fit is wrong. No, that's required in many cases because of mounting and dismounting conditions and because of the locating, non-locating behavior we want to get in a bearing application. But we need to be aware that when the surfaces are not, let's say, cylindrical enough, they don't have the right tolerances, these may develop, and if you don't, let's say, repair these surfaces on the housing or the shaft properly, this will only get worse over time. So it's not enough to polish this away from your bearing shaft or your housing. Here, for example, we see the characteristic feature of fretting corrosion that develops into the load area of the bearing and not in the unloaded area that would be located in the picture towards the left. So this is an outer ring mounted with a loose fit, and then you only see the fretting corrosion in the load area. Because to generate this phenomena, you need to have this micro movement situation, which also is connected to this idea of a loose fit. there is some micro movements, not rotation of the ring, but just micro movements at a local level. And together with the oxygen, the particles will form oxide and also increase in volume and make the situation worse very quickly. False Brinelling is a failure, like in this case, the outering of self-aligning ball bearing. And you see that also here we could identify the distance between the running elements that have created a kind of nest in each position. And this is when machines are exposed to heavy vibrations. There will be a wear process, removal of material, and the damage can be much more significant in ball bearings as compared to roller bearings, and also in bearings that are standing still as compared to bearings that are running. This example is just to confirm that on a cylindrical roller bearing, what we see here in the picture, if we look carefully, is that there are some of these marks that have more depth, and they also have the distance between the running elements. But we also see many other smaller marks. So we can conclude from this initial assessment that the vibrations that were creating this false Brinelling damage was happening when the bearing was standing still, but also when it was operating. So there are many more irregular marks. And one of the things that help us to distinguish this is the discoloration. They tend to be reddish and sometimes shiny at the depression of the wear that is being generated. Excessive voltage, it's a problem that, of course, can happen when typically when repairs and welding is being done and the electricity flows through the bearing. In this example, we see a very strange phenomena that the electric current has created this zigzag on the surface of the ball and the outer ring of this ball bearing, but you will also see something similar on the inner ring because it has to go all the way through, and some more spots here. What will distinguish this, when you look with some amplification, is the molten characteristics of this depression, these craters. And even if in some cases the current leakage that you may have, I would say very common in electrical machines, motor and generators with variable frequency drives these days. Sometimes this can be so mild that it's hard to distinguish from other failure modes. And you might need to go down to the material analysis level that we see in this picture, where a treatment of the surface was done to distinguish between the rehardened areas on the surface, which are much harder than the base material, with the annealed areas below that are softer than the core material. So this will be, let's say, a confirmation that the damage was created by current leakage going through the bearing. Overload in this example is generated because of maybe a mounting problem. The distinguishing feature here, even though there is material that has already been removed, so we, because of the amount of spalling, we have lost part of the evidence. But what we can say is clearly that it was a damage that was created with a bearing at standstill, because of the distance between these areas is coinciding with the ball pitch, and also that there is a certain axial displacement from the center, which seems to indicate that this could have been generated by deformations and indentations created during mounting of the bearing, which means that the force was applied through the running elements. Indentation from contamination, I mean, we mentioned contamination before. We see an example of the inner ring of a taper roller bearing inner ring raceway with lots of the plastic deformations. So there was a significant amount of hard particle contamination in this case. And of course, this will feed itself because more particles will wear off and they will wear other parts of a bearing, generating more contamination in a vicious circle. Indentations can also be generated because of handling, like in this inner ring of a cylindrical roller bearing, typical example of electric motor assembly, where the inner ring is mounted on the rotor, the outer ring and rollers are mounted on the cover, and then they have to be put together. But because the clearance between the rollers and the raceway is so small, it's very, very easy to generate small scratches or dents that will be the areas of stress concentration where the failures will develop later. Most of the time, the noise will reveal that something is wrong with the bearing when the motor is tested. And the last few, we are already reaching our time, so we are going to mention force fracture, in this case the inner ring of a spherical roller bearing, which in this case what happened is that the bearing has a taper bore and the interference between the inner ring and the shaft or the sleeve where it's mounted is produced by driving up the inner ring onto the taper. And if the drive up or the axial displacement is excessive, the expansion of the ring will reach the limit of the material strength, and then it can develop into a fracture. This picture here shows a fracture of an inner ring of a taper roller bearing, but the fracture here, this is a very good example where you see the initial surface fatigue, and of course the ring was already fractured, but when we start looking at the fracture, we notice something irregular. We remove part of the broken ring, and then we see actually that the fracture started and it was growing from the fatigue area until reaching a point of fast development where the fracture of the ring was generated. And we should never forget that the ring, the inner ring, is the one that is most commonly exposed to heavy hoop stress, which then is an added factor that will help the development of this type of fracture. Finally, the thermal cracking, it's another process that can happen between the side face, like we identify here, the side face and a component on the shaft, a spacer, another machine part that is rubbing under load against the side face of the bearing. There is a cold welding and transfer of material process happening. And out of those areas, the cracks will start to propagate in axial direction that may grow into a full fracture also. I mentioned this before. I mean, we need to look at the bearing as part of a system. So we need to look at the lubricant, at the shaft, at the housing, at the seals. We need to look at everything around and even the other bearing on the same machine, or other bearings if we are talking about more complex machines like a gearbox. So we should never look at the bearing in isolation. There is a lot of material that it's available. We have in our webpage a catalog that covers what we have seen here today. So we will post a link to this material. You can download this from that link. You can also buy the standard from the ISO webpage, the 15243. And there is more publications that you will find. This is a very traditional one from a former SKF engineer, Italian. that was written and reprinted several times, the failure atlas in Hertzian contact machine elements, covers, bearings, and gears, basically. But one of the things that we should remember, like I said at the beginning, if it is too late, it's too late. And if you let the bearing run to this condition, it's impossible to know what was the reason, how this bearing reached this level of damage, including the cutting with a torch that will destroy part of the evidence. So always remember, try to get the bearings at the earliest possible indication of a failure. With that, I finish my part. I want to thank you very much for your attention.